Welcome to this tutorial in which we are going to handle topic number 39 according to our physics syllabus as given by the KICD, which is basically photoelectric effect. That's what we're basically going to handle, and I'm your tutor, Dr. Joseph Adeli. So before we begin, let's have a quick word of prayer. Father, Lord in heaven, we invite you in this session, you being the greatest physicist you've ever known. We ask for your guidance in this particular session, that you're able to understand all that you're going to be able to take. In Jesus' name I pray, amen. Quickly to our specific objectives that we ought to be able to cover, and I believe you are working by checking on them so that you're able to know where you are going and where you have come from and where we are. So by the end of this topic, you should be able to perform and describe simple experiments to illustrate the photoelectric effect. Basically, unless you have all the parameters or the apparatus, you can be able to do this. But for the situation at hand, you should be able to understand basically with the theory behind everything, and you should be able to be acquainted with the concept about photoelectric effect. Number two, you should be able to explain the factors affecting photoelectric emission, which we're going to do in some upcoming tutorials. What we're going to do in this tutorial is that we are going to apply the equation E is equals to HF to calculate the energy photons. Later we shall be able to define threshold frequency, work function, and the electron volt. And the instance equation shall come in the next tutorial, and should also be able to explain the applications of photoelectric effect as the final part of this topic. Solving numerical problems shall be a part of us, which shall be part of our backbone. We know that physics and mathematics share very many things in common, so it's something that is a constant, that both of them shall, the numerical problems shall always be there. Beginning with a very small background in this tutorial, sorry for that, we shall be able to cover about light energy and quantum theory. So beginning with a little background, at the end of the century, many physicists felt that all the significant laws of physics had been discovered. They were quite satisfied that at least we have gotten everything. So the question is, were they trying to relax or being lax on some particular things? We don't know. That is not stated. So a physicist by the name Hertz stated the wave theory of light is, from the point of view of human beings, a certainty. So he was saying that the wave theory of light is basically certain. So he was kind of proving that light also behaves as a wave. That's what he was saying. Now that view was soon to change. Around the year 1900, the photoelectric effect was discovered. The emission of electrons by a substance when illuminated by electromagnetic radiation. So that's what they were yet to discover at that particular time period. So careful study of the photoelectric effect was performed by many scientists. Now the wave theory could not totally explain the photoelectric effect, but a variation of the old particle theory could. So about the old particle, whereby you are focusing on things as particles and as packets, that's what could be able to explain the photoelectric effect. So we have a physicist by the name Max Planck and Albert Einstein subsequently proposed the quantum theory. So we have, that is Planck and that is Einstein. So they both subsequently proposed the quantum theory, which basically introduces us to something here. The quantum theory, we should know that Max Planck in the year 1901 came up with the idea that light energy is propagated in small packets of energy. And for him, each packet is called quantum of energy. Okay, not for him. Sorry for that mismatch of grammar. Find that each packet is called a quantum of energy. In plural, we find them, it's called quanta. And basically, in light, these discrete amounts of energy are what we call photons. So those discrete amounts of energy are what we term as photons. So basically, in a nutshell, the transfer of energy between light radiation and matter occurs in discrete units called quanta, the magnitude of which depends on the frequency of radiation. That's what basically was brought about by this quantum theory. Although we still characterize light as a wave, it is actually neither a wave nor a particle. It seems to have characteristics of both the particle and the wave. So it doesn't contradict either of them, but it says it's like I'm part of both of you. The modern view of the nature of light recognizes the dual character. That is, light is radiant energy transported in photons that is guided along their path by a wave field. I believe you can see the correspondence of the two. So it's a radiant energy transported in photons, and photons, you have said, is the discrete amounts of energy that is guided along their path by a wave field. So both of them interrelate to be able to come about light. So picking up now on this, light energy and quantum theory, how do they now come about? According to Planck, the energy E, that is basically the way we denote energy in terms of physics. The energy E possessed by one photon is given by E is equals to hf, of which E is energy, h is Planck's constant, and f is frequency. Let's explain what they are. Where h is the Planck's constant, equal to 6.63 by 10 power negative 34 joules second, and f the frequency of the radiation. So that's what we have there. So h is basically a constant that was discovered by Planck, and you basically use it the way it is, and frequency is dependent on the wave of basically the electromagnetic radiation that is being used. Something else we should be able to note is that from the general law of wave equation, c is equals to f lambda. Now what is c? C, you basically know it's the velocity. But velocity of what? C is the specific velocity of light. I've used the term specific. Specific usually terms 1 kilogram. So let me not confuse you more. I'm not speaking of 1 kilogram here. I'm simply speaking of light. The speed of light is what you term as c. It's a way of denoting the speed of light, or the velocity of light if you like. So basically, it is basically frequency, the product of frequency and lambda, whereby f, is frequency and lambda is wavelength. Hence, we know that frequency is equals to the speed of light divided by lambda. So substituting this into Planck's equation, you find that thus E is equals to hc over lambda, where c is the velocity of the radiation in a vacuum and lambda is the wavelength. So since c is the radiation, c of the radiation and the Planck's constant h are constants, a radiation of longer wavelength lambda has lower energy. Now let's explain this in mathematical terms. We know that E is equals to h c over lambda, as we saw previously. You can even see it here. So because h and c are constants, I decide to omit them into this equation. Now if you omit any constants in an equation, the equal signs disappears and is replaced by a proportional sign. So this is what we have. So this statement simply means E, which is energy, is inversely proportional to wavelength. So it means the higher the wavelength, lower the energy, and the higher the energy, the lower the wavelength. So this is what this statement means. The radiation of longer wavelengths has lower energy. I believe this statement helps to explain that. Or you can also apply this equation whereby E is equals to hf. So if I omit the Planck's constant, we have energy is directly proportional to frequency. So the higher the frequency, the higher the energy. The lower the energy, the lower the frequency. That's what we have. You need to understand those particular proportions. Let's have an example before we wrap up our tutorial and be able to call it a day. Try working out with this question. You may pause the video if you don't mind. Compare the energy contained in a photon of red light of wavelength 7.0 by 10 power negative 7 meters and violet light of wavelength 4.0 by 10 power negative 7 meters, taking Planck's constant to be 6.63 by 10 power negative 34 joules second and C as 3.0 by 10 power 8 meters per second. Supposing that you have something at hand to table, I'll begin with mine. Basically, to answer any question, you have to interpret that particular question. First, write all the numerical data that are required of you. So these are all the data that are given in the question. We have the wavelength of the red light, the wavelength of the violet light, the Planck's constant, and the speed of light. So beginning with the red light, E is equals to that particular formula, the product of Planck's constant and the fraction of speed of light and wavelength. Hence, if I substitute everything correctly, I'll end up with my energy as 2.0 by 10 power negative 19 joules. For violet light, the formula still remains the same. Hence, if I bring out my substitution, I should have that my energy is 4.9 by 10 power negative 19 joules. Now notice here, the lower the frequency, the higher the energy. The lower the energy, the higher the frequency. That's how that statement was meaning. So hence, a photon of violet radiation contains more energy than that of radiation. That's what we figure out in this particular statement. So basically, this is where we shall be able to pause by, after understanding about light energy and quantum theory, of which it was basically telling us that when we are relating to photoelectric effect, you may not directly relate it to the way we relate it to light and other particular electromagnetic waves and other things. Photoelectric effect is whereby we shall look at propagation of propagation of light energy in terms of packets, and each of those packets is what we term as quantum or basically quanta in plural, and these discrete amounts of energy are also termed as photons, and we also have that particular Planck's equation. So in the next tutorial, we shall look at Einstein's equation of photoelectric effect and be able to explain more parameters related to it. Otherwise, success in your preparations, and may God bless you abundantly.